We'll begin an introduction to counting by asking the question, just how many are there in lots of different situations, and you might come to understand that counting is not quite always as simple as it might seem. Let's start off with a simple example. Suppose I flip 3 coins, a penny, a nickel, and a dime in that order. If I began with the penny, it can either be heads or tails. Then I want to flip the nickel. If the penny were head, then the nickel could either be head or tail. If the penny came out to be tail, the nickel could still come out to be heads or tail. Now I want to flip the dime and notice every possibility. If the penny is a head and the nickel is a head, then the dime can still come out to either be a head or a tail. On the other hand, if the penny is a head, the nickel's a tail, the dime can still come out to be either a head or a tail. Each one of those is generating a different possibility. For example, if I go down this what's called a branch, I'll get head, tail, tail. If I had gone up one for the dime, I would have had head, tail, head. Every time you go down what's called a branch, you get a different possibility. So as I continue, suppose I start down this branch. The penny's a head, tail, the nickel's a head, then the dime could still be either a head or a tail. That generates the possibility tail, head, head, but it also generates the possibility tail, head, tail. And continuing, if the penny is a tail and the nickel is a tail, the dime can still either be a head or a tail, and that generates the possibilities tail, tail, head, and tail, tail, tail. So when all is said and done, there are 8 different arrangements of heads and tails possible. And you can actually list them if you're interested in doing so. There are 8 of them, and you get them by going down the branches. This structure has a name. It's called a tree diagram. As I said, it's made up of branches, and each branch gives you one possibility, and then you add them up to count how many total ways there are of doing whatever you're doing. It's a brute force method, but the nice thing about the tree diagram is if you do it carefully, it's very difficult to accidentally leave out a possibility. So anyway, that's a tree diagram. Let's use it in yet another example. Here you're taking a 4-question true-false quiz, and I want to know how many different ways there are to answer all 4 questions. Let's use the same strategy with the tree diagram. We start off with question 1 can either be answered true or false. So there are 2 ways to do that. Once you answer question 1, you branch again. So suppose question 1 were answered true. At that point, you still have 2 ways of answering question 2, either true or false. Conversely, suppose you answered false for question 1. Nevertheless, you still have choices of either true or false for question 2. Generates another series for your branch. Now let's move on to question 3. You've already done 1, you've already done 2. Question 3, every time you hit the tip of a branch, since each question can be answered true or false, you have 2 more possibilities. So as you can see, each branch continues out by doubling each time. Once you get the pattern down, you'll notice the same thing follows for question 4. At each branch point, you have 2 possibilities. If you count, you'll see that there are 16 different ways to answer all 4 of those true-false questions. And you could actually enumerate them if you wanted to. If you go down a branch, you get a possibility. So if you start off T, 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 you could answer all of them true. You could answer the first 3 true and the last one false, and so on. You could answer the first 2 true and the third one false and the last one true. You could answer true, true, false, false. You could answer true, false, true, true. And as you move down the branches, you generate all 16 possibilities. So there are 16 different ways that you could answer a 4-question true-false test. Let's move on to something that requires maybe a little bit more thought. This example says, list all the ways that 2 members of the set consisting of the elements A, B, C, D, E can be selected if repetition is allowed and the order of selection is important. You've got to pick up on the cues here. It's important that you're only picking 2 out of the 5. It's important that you can repeat letters. So if you choose A, you could choose A again for the second time if you wanted. And the order of selection is important. So if you chose A and then B, that would be a different selection than if you chose B followed by A. So all of these little cues are important and you have to pick up on them. Having said that, let's go through the example. In the beginning, it doesn't matter. You can choose A, B, C, D, or E. Free choice. Now, if I start off looking at A, there's no reason why I can't choose A again because it says repetition's allowed. So I can choose A again, or I can choose B, or I can choose C, D, or E. So there's really no restriction at all because I can repeat. If I move along to B, of course that's 5 different ways. If I move along to B, I've got the same set of options. Because B can be repeated, I can go B, B, and also the order of selection is important. So even though I've already chosen A, B over here, I can choose B, A because A and B and A are considered to be different. And that's what the order of selection being important means for us. So the bottom line is I have a free choice of A, B, C, D, E again. I can choose B again because repetition is allowed, and I can choose A again because A, B, and B, A are considered to be 2 different selections. Let's move to C. Same idea. I can choose C again, and the order does matter. So even though I've already chosen AC and BC, I can choose them again as CA and CB because order matters. By now you've sort of seen the pattern. It's going to follow through for D and E. I've got free reign for both. So when it's all said and done, I have 5 plus 5 plus 5 plus 5. 25 different ways that this selection can be done, choosing 2 members from 5, allowing repetition, and having the order of selection be important. Just to emphasize how important these cues are, I want to do a similar problem with a slightly different phrasing. This time, I want to list all the ways that 2 members of the set containing the elements A, B, C, D, and E can be chosen if repetition is not allowed. So this time we're not allowing repetition. The order of selection is still important, but we don't allow repetition this time. Well, what's the effect of that? In the beginning, nothing. You can start off with any of the 5 letters. But looking at A, I cannot repeat. So I can't use A again. That means I can only choose from B, C, D, and E. So instead of having 5 ways, I only have 4. Okay. Moving along to B, I can't choose B again, but the order is still important. So even though I've already chosen A, B over here, there's nothing wrong with me choosing B, A, because the order of selection is still important. That means that the only thing I can't use again is B. So when I branch again, I will have to leave out the B. So I'm going to choose A, C, D, and E. But that's still 4 more ways. Now move to C. there's again, I have to leave the C out, but since I can reorder and get a different selection, then that's the only thing that has to be left out. And by the time you get this far, you can see that the same pattern is going to hold for D and E. Going down the D branch, I have to leave D out, and going down the E branch, I have to leave E out, but there's still 4 ways. So in the end, there will be 4 plus 4 plus 4 plus 4, which is a total of 20 different ways that this can be done. Notice the wording matters. Let's vary it one more time. This time the problem says list the number of ways that 2 members of the set containing the elements A, B, C, D, and E can be selected if repetition is allowed. So we're back to allowing repetition, but this time the order of selection is not important. That's different. This time we're not allowing a change in order to be a different selection. So if I choose AB, I can't choose BA. They're considered to be the same. As we start off in the beginning, it doesn't matter. You still have a choice of all 5 letters A, B, C, D, and E. Starting with A, repetition is allowed, so I can choose A again. So I have 5 choices. Any of them can be chosen. But when I move to B, something slightly different happens. Repetition is allowed, so I can choose B again. Just because I chose B once, I can still choose it again. But this time the order of selection is not important. So I have chosen AB over here, so I'm not allowed to choose BA. So this time I can choose B again, but I can't choose A again. So that leaves me with just 4 ways to choose the second element of that set if B is the first one. I can choose B again, but I can't reuse A because AB and BA are considered to be the same. When you move to C, notice what happened. Notice what's happened. I've chosen AC already, and since order is not important, selection order is not important, I can't choose CA. And since I've already chosen BC, I can't choose CB. Well, that knocks out 2 possibilities from the 5. So now I can choose C again, and I can choose D and E, but I can't reuse A and B because if I put an A in, that'd be CA, which is the same as AC, and if I put a B in, that'd be CB, which is the same as BC. I think at this point you sort of see the pattern. If you move to D, you're not going to be able to reuse A, B, or C. But you can reuse D, and of course you can use E. And when you get to E, you're not going to be able to use A, B, C, or D, but you can use E again. And you can see what's happening. It's counting down. So 5, 4, 3, 2, 1. And that's because the order of selection is not important. So when all's said and done, if you add 5, 4, 3, and 2, you'll end up with 15 different ways that this can be done. So these little cues in the problem are important, and if you don't read carefully, you're going to make a mistake. So read very carefully when you're doing these problems and don't rush through them. Let's change up a little bit and do a problem with rolling 2 dice. Let's suppose the first one's red and the second one's green. The question is, how many different rolls are possible? Now you can do a tree diagram with this if you like, but it gets a little unwieldy because the first branch has 6 possibilities and the second branch has 6, and it's very unwieldy to draw. My suggestion when you're working with rolling 2 die, I would suggest doing it as a rectangle. Actually, in this case, it's a square. If you put the red rolls as row headings and the green die possibilities as column headings, you can generate every possibility by simply putting the red number first and the green number second. So if you've got a 5 here and a 3 here, you can see you can generate every possibility of pairing a one outcome with a red outcome with a green outcome. And it only takes a glance to see that this is a 6 by 6 rectangle, which is actually a square, 6 by 6. So there'll be 36 entries in this table. So there are 36 possible combinations. Every entry in that table represents a different row, and there are 36 of them. Let's ask a slightly different question. We have the 36 possible rows. Now I want to know, in how many ways can you roll a sum of 9? Once you have the 36 possibilities, that's extremely easy to answer. You simply look and see what sums to 9. As you can see fairly easily, those 4 circled combinations add up to 9. It's also easy enough to see that if you move this way, your sums get to be less than 9, and if you move this way, the sums become larger than 9. So there are only 4 possibilities. Once you have that 6 by 6 square, those sorts of questions become really easy to answer. So there are 4 ways to roll a sum of 9.